So good afternoon, everyone. And first of all, I would like to thank the organizing committee for inviting me. I'm very pleased to be here today. So I'm sorry this is the perfect time for having a nap, especially that some of them are jet-lagged, I know. But instead, I would like to entertain you about GNU Guix. So it's pronounced Guix, which is, I guess, quite unusual, which is a functional GNU/Linux distribution. And it's also a scheme library, which is why I'm here today. So a few words about me. I work as an engineer at INRIA, which is a French research institute, but Guix is something I do besides my day job. And Guix is essentially, it's a free software project. It's rooted in the free software world. It's part of the GNU project, which you've probably heard of. And so it's a fairly young project, like 4 years old, but currently there are between 30 and 40 contributors each month, so it's taking off, I would say. Guix is a functional package manager, and on top of that functional package manager, we've built a whole system distribution, which is called GuixSD, the Guix system distribution. So if you've heard of Nix and NixOS before, the high-level view is kind of similar, right? These are two functional package managers and distributions. So what I would like to talk about in this talk is mostly about how Guix uses scheme to build everything, and how it uses it in different ways, in unique ways. So first thing, to build embedded domain-specific languages in scheme and to basically build the whole distribution around those domain-specific languages. And second thing is how we use Guix in other components of the distribution, and how we do code staging in scheme. But before I get into those details, maybe I just give a brief overview of what Guix is and what functional package management is. Oh, so a quick demo to begin with. Okay, so Guix is a package manager that you can use on top of your GNU Linux distribution, or you can also install GuixSD, which is a standalone GNU Linux distribution. So let me just give a quick demo of what it feels like to use Guix. So basically, you have one main command, which is Guix, and you can search for packages. So we try to keep the command line UI quite simple. So you can search for packages, the typical thing you would expect from a package manager. So there are lots of things related to scheme, some of them which are not scheme implementations at all. But anyway. And from there you can install packages. So this is all going on as an unprivileged user. So let's say I can install Guile. Okay. And yeah, the tool is telling me about environment variables that I need to set for things to work properly. So I don't know about you, but I know that I've spent a big time of my life figuring out what environment variables need to be set, so I'm always happy that there's a tool that can help me with that. So in the case of Guile, I have to set up this Guile compiled path library. And now I can perform a new transaction saying, let's say I want to remove Guile and install Python in a single transaction, which is a weird thing to say, but it's a toy example. And this time, I would need to set a Python path environment variable. Okay. From there, I can query the generations of my user profiles. So what this is telling me here is that I have two generations. The first one contains one package, which is Guile, and the second one contains one package, which is Python. And so what I can do from here is that I can roll back. Okay, and now I no longer have Python installed, right? So I can query the list of installed packages. So this is the basic of how you would use Guix in your daily life, right? Yes, you can actually switch to any generation, not just the previous one. So rollback is a shortcut for switch generation. Okay, so this is a basic idea, but since we have a tool which has information about all the packages in the distribution, we can actually extend this tool to build, more useful things. So let's say you want to hack on Guile or, some other piece of software. Well, if you want to get started manually, you have to install, a whole bunch of things, which is kind of boring. It's especially boring since actually Guix knows all about this dependency graph, right? So why would you do it by hand? So instead, we provide a different tool, which is called Guix environment. And so if I run Guix environment -- container Guile, then it's going to create a Linux container that contains everything needed to work on Guile, to compile it, etc. So if I look at the path inside of it, I have only 2 automatically generated directories in there. And, well, basically I have only the things needed to build Guile. So if I look at the include directory, I have like libunistring, the C library, stuff like that, and nothing more. So that's quite convenient. So this is a basic idea. Now the foundations of it are not new. The idea of functional package management goes to the Nix package manager. And especially if you look at this paper from 2004 by Elko Dolstra and a few other people. One of them is in the room, I think. I don't know if you were... No, okay. The idea here is to basically draw a parallel between what we're doing in functional programming languages and how we can deploy software. So essentially, we would view the build process of a package as a pure function. That's the main idea, right? So when you're building and installing a package, you're running configure, make install. And what we're saying here is that configure, make install, this is a pure function. It takes a number of arguments, like it takes dependencies, like you need GCC, you need a C library, and so on. These are the arguments of your function. But then, let's assume this is a pure function. So you give it the same compilers and library, you run the same configure, make install command, and you get the same result, right? And so once we have it, if we look at the set of built packages on your system, it's essentially a graph, and it's viewed as a persistent data structure, a persistent graph. So this is the main idea. So how do we do that in practice? Well, so in the case of Guix, what happens is that we have, on the right-hand side, we have a bunch of scheme modules in which we define package recipes. And so we have high-level package recipes that we compile down to low-level derivations, where a derivation is a low-level set of build instructions, essentially. And then we make remote procedure calls to a build daemon. And this part is inherited from the Nix project. And from there, the build daemon can actually create isolated build environments. So it will automatically spawn, every time you build something, it will spawn an environment in a CH root with separate user IDs and so on, such that your build process cannot possibly refer to things that were not declared as part of its inputs. So if you have a build script, for instance, that tries to use /user bin Perl, and you didn't provide Perl as an input to your package recipe, then it's not going to be able to use Perl, right? So you cannot have undeclared dependencies. And essentially, that's how we get that vision of a build process as a pure function. Then, how does it work in practice? What value do we get when we build a package? Well, let's assume we want to build chibi-scheme with Guix. Well, we run that Guix build command, and what we get as a result is a file name like this one, starting with GNU store, then a big hash and chibi-scheme. And inside that directory, we have the chibi-scheme installation. So the hash here is actually a hash of all the dependencies leading to chibi-scheme. And by all the dependencies, I really mean all of them. So that includes libraries, compilers, build scripts, and so on and so forth, and recursively. So from there, we can do memoization. You know, it's typical functional things. So when I run that command, maybe it will build it because I don't already have it in store. Or if I already have it in store, then nothing needs to be done, right? The software is already there. So if I run that command 2 times, the second time, there's nothing to do. Memoization. Then in Guix, we define high-level package recipes like this one. So, you know, without being a scheme expert, I think anyone can recognize what this means. We're just, you know, describing the package, how it needs to be built. So this GNU build system thing means configure, make install, you know, that kind of thing. So this is actually scheme, but the good thing is that people don't need to realize that it's scheme. And that's why we managed to have a contributor base that is relatively large if you compare the scheme community, because people can actually start packaging without realizing that this is scheme. And our ulterior goal is to turn these packager people into scheme programmers without them noticing. So that's the idea. Right, so, but since this is scheme, well, we get the full power of scheme. So this is Emacs running with Geyser, which is the Emacs Guile bridge, right? So Geyser can talk to a live Guile running, and so it knows everything about what's going on here. So it can tell me that URL fetch here is actually a variable defined in that module. You know, it knows everything about the code that's here. And essentially, that package form, in terms of scheme, is a macro that expands to a big make struct call. I think I can expand it here. All right, so it's a bit intimidating, but basically what's happening here is that at the end we get, you know, a bunch of make struct calls here, which means I'm just instantiating a record of that type. And that's it. So we have a package abstraction, which is pretty useful. Then the question is, how do we define dependencies in package recipes? Well, we simply add an inputs or a native inputs line here, listing the list of dependencies. And in this example of grep, well, Perl, we see that grep depends on Perl, and Perl itself is also a package object, right? So we could jump to its definition. This one, okay? So this is all scheme, and we can browse all those package objects from scheme, which is quite convenient for a number of applications. Okay. So this is scheme all the way down. So if we look at a more complete example, well, this is the example of Perl. I'm just continuing that one. Well, we can see that it's using the GNU build system here. So GNU build system means configure, make install. Except that we need to customize it, right? Because, you know, Perl has its own arcane build system, so we need to somehow adjust. And so what we are doing here is that we are providing additional arguments to the build system. And you can see this is quoted code. But in fact, what we are doing is modifying the set of build phases. So we are saying, I want to replace the configure phase with this particular lambda, which does things differently. I mean, we don't need to go into the details. But so again, the build side of how we build the package is also configured in scheme. I will get back to that later. But why stop here? So we can also describe a complete operating system configuration as a scheme object. So this is an example. You know, again, this is purely declarative, and again, we're just building a record that contains all the details about the operating system configuration, the file systems, user accounts, and system services that are running on the system. So this is my configuration file. And from that configuration file, I can actually instantiate it. So I can say, so first of all, I can say, let's build, this is not the right one. Let's build my scheme machine, so to speak. So Guix system build is just going to instantiate that operating system. And I'm going to get a value. You know, this is the value I'm getting. Oh, and this is an Emacs mode that's showing ellipsis. Right. We have an Emacs mode that actually hides those big hashes because it can be boring sometimes to see all those hashes. So here I'm getting that value, and if I look inside of that directory, well, there's just a few files here. All of them are symlinks. So we have a symlink to the etc directory of that operating system instance, for instance, with a bunch of files that you would expect. We have a symlink to the initial RAM disk, a symlink to the kernel, you know, that kind of stuff. And we also have a boot script, which again is actually a generated piece of scheme code, which is the boot script that is used when we boot the system. And going further, if we look at that initrd file from there, so the initial RAM disk is what the Linux kernel uses to boot the system, right? You give it an initial RAM disk, and the initial RAM disk is responsible for mounting the root file system in particular and doing other initialization steps. And if we look at that initial RAM disk, well, guess what? There are a number of files in it. It's a CPIO archive. And inside of the initial RAM disk, we also have Guile and a bunch of Guile modules. Right? So what this means is that right from the start, when we boot the system, we get Guile code running inside the initial RAM disk. So to summarize, when we boot the Guix SD, so the Guix system distribution, what we get is that we have the Linux kernel, and then we have an initial RAM disk, and it runs Guile. And then we have the initialization system, which is called the GNU Shepherd. It's also written in Guile scheme. And from there we have applications, which, you know, may or may not be written in Guile. So we have several layers of scheme all around the place. Which brings me to my next topic, which is code staging. So since we have scheme code in very different places, we need ways to generate scheme code that is going to be useful and that we can run in those different stages, right? So if you remember that diagram here, we already have two stages of scheme code. So we have one stage on the right-hand side, which is where we have those defined package forms, right? And on the left-hand side, we have scheme code that essentially runs commands like configure, make install, plus does a bunch of other things to, you know, to actually install the package correctly. So we already have two stages here. So the question initially when we started the design of Guix was, how can I use scheme on the build side as build side code, so on the left-hand side, you know, to write the build phases of my packages. So essentially, I want to be able to write a build phase like this. Let's say I want to do a simple derivation, simple build action, which consists in creating a symlink from the core utils package to the output. Right. So essentially, I would like to write something like this, except that, of course, I'm not going to write those long file names by hand. That wouldn't be very convenient. So we need a way to say, actually, here I'm interested in the file name of core utils, and here in the file name of the result of my derivation. So how do we do that? So the first approach looked like this. So what's going on here? Essentially, we have that build expression to derivation, to which I'm passing that S expression above. And somehow, this procedure creates global variables around that expression I gave it, right? So it creates a build inputs global variables. And up there in my expression, I can refer to that global variable, and I can say I want the file name that corresponds to the core utils label. And the core utils label is given here, right? I'm just giving some sort of an A-list that maps labels to packages. So core utils here refers to a package object. Yeah, and from there I can get access to my core utils file name. And likewise for the result, for the file name of the result. So it does the job, but it's pretty cumbersome and verbose, so not great. And on top of it, it's actually error prone. So suppose you forget to pass those inputs here, down here, right? So you still have your build expression up there that refers to something, except that this asocref thing is going to return false because I forgot to pass the core utils input down there. So, you know, at compile time, everything will go fine, but if I try to actually build that derivation, then I will get an error when I build that derivation. It's a bit too late to get an error. What we would like instead is to get an error right from the beginning, you know, as soon as possible. Plus the fact that we need to carry this list of inputs, you know, in different places, it's a bit redundant, right? Plus we have these unhygienic global variables, so, you know, this was not so great, right? We needed a better way. So that brings me to the second and last attempt to date, which is called G expressions. So I think the G was not taken yet, so I thought I could use it, right? Let me know if there is prior art on G expressions. So G expressions or GEXP work like this. Essentially, it's like quasi-quote and unquote, right? But with additional, you know, contextual info. So you could think of GEXP, the GX form here, as quasi-quote and unGEXP as unquote. Except in this specific case where we're referring to the output of the result, and there's really no variable that contains that refers to the output of the result. So this one is unhygienic in a way, but you know, it has to be. So what I'm saying here is that, okay, I want to call my symlink procedure, and the first argument must be the file name of core utils. And again, core utils here refers to the core utils variable, which is a package object. And from there, I can call the new GEXP derivation procedure, and I just give it a name and the GEXP, and I get the result. So we no longer have that redundancy between, you know, where we had to specify inputs in two different places, basically. So every time I use that G expression, it always carries information about the dependencies that it expects, right? So the GEXP object is a first-class object that carries all the necessary information about dependencies. So that's pretty cool. And we have a shortcut for that. Hash tilde is for GEXP, and hash $ is for unGEXP. I think these were not taken yet either, but, you know, we never know. Okay, and of course, the G expression itself is independent of the system you're targeting. So if I want, let's say I'm on a 64-bit machine. So if I'm building natively, I'm getting this file name, 123 core utils. But if I'm building for a 32-bit system like this, then I'm getting a different file name in the build script, right? Okay. So this is a basic idea of G expressions. But again, if we compare with quasi-quote and unquote, so we have GEXP and unGEXP, but we actually need more if we consider cross-compilation. So Guix can already do cross-compilation of packages. So when doing cross-compilation, we need to be able to differentiate between native inputs and target inputs. So in this toy example here, I'm using the ln command of coreutils to create a symlink. A symlink from the Emacs command from the vi command, to Emacs. And what I mean to say here is that I want to use the native ln command if I'm in a cross-compilation context, right? So again, if I'm doing native compilation, so we have this hash plus thing here, which is like $, except that it means unjexp native. So again, if I'm in a native compilation context, it doesn't make any difference. $, and hash plus are equivalent. But now, if I'm cross-compiling, let's say to MIPS, then I get different file names for these two target inputs, Emacs and the output. But I'm still using the same coreutils because I'm using the native coreutils, right? So this is cross-compilation. So the next thing here is modules. So when we are doing staging, the whole point of using scheme, in different places is that we can share code. So obviously, we want to be able to factorize common code in modules, and we want to be able to say, I'm writing a G expression, but this G expression needs to use some guile module. So let's say I'm using the Guix build utils module so that I can get this wonderful mkdir-p procedure. Well, if I just do that and try to build the derivation, I'm getting an error because Guix build utils is not in the chroot environment, right? So I need a way to express which modules need to be imported. And so for that, we have a special form, which is called with imported modules, unsurprisingly, where we say, well, the following G expression in this lexical environment needs the Guix build utils modules in its environment, in its chroot, right? And so that's how we handle modules. So this is especially useful if we start to go to more complex use cases. Like let's say we want to build a scheme script that uses our Gremlin module. So Gremlin it's actually a module that we use to do verification on ELF files. So one of those verifications is making sure that everything an ELF file requires, so everything that is in the need field of an ELF file, is also in its run path. Okay? So let's say I want to build a script that does exactly that using this module. Then I can say with imported modules, but I can also ask for the whole closure of that module to be imported. Because Gremlin itself depends on other modules, right? So I need all of them to be available in the environment of that script. And from there, I can actually generate the script, and the script will automatically have its load path pointing to the right modules, which is convenient. And again, if we go to more complex use cases like the initial RAM disk that I showed you before, well, we want to make sure that the initial RAM disk contains all the modules that it needs to actually, run its boot code, right? So that it also comes in handy here because the initial RAM disk is automatically populated with all the modules that we need. Okay, so in those examples, I'm always showing unjexp and the package object, like unjexp coreutils. And this is how we define GX compilers. So a GX compiler essentially is a procedure that takes a high-level object, like a package object, and compiles it down to the low-level representation, which is called derivation, right? So this is how we handle packages, but we can extend it with other types. So let's say I want to define a new record type. Let's call it plain file, which takes a name and the content of the file as a string. Then I can write a GX compiler for that file. That compiler will simply let's say, intern that file into the store, into that GNU store directory. And so we can build basically arbitrary records like this and have them be handled automatically by the gexp code. Going further, we can also define how those ungexp are extended. So one common idiom when referring to a file inside a package is this. We write #tilde string append $$ bin ls, and that means we're essentially generating code that looks like this, right? Which allows us to refer to the ls file inside of core-utils. So it does the job most of the time, but sometimes instead of generating a string append expression, we would prefer to generate directly, the file name entirely. So again, we use compilers for that, gexp compilers. We define a new file append record type with a special expander in addition to its compiler. And the expander says, I'm going to concatenate the file name that corresponds to this package to that string, right? And this way we get directly the string that we would like to have. A few words about the implementation. How much time do I have? 10 minutes. So gexp is a macro, right? There's no magic here. It instantiates a gexp record type, and then we have a gexp to sexp procedure internally, which creates the s expression that we want to have in our build script or in our initrd and so on. So let me give an example. Okay. So this is a G expression. I forgot something. So what happens when we extend it? Well, this is what we get. And again, we're just getting a make struct at the end that creates a record of the gexp type. And that record contains information about the references, so the core-utils package that we depend on, about the modules that we need. So here it's the empty list. And then a procedure. So the procedure that we're getting here is the procedure that will generate the S expression, right? So it takes one argument here, which is going to be the file name of core-utils. And from there, it essentially injects that file name inside the S expression, right? So it's a pretty fast way to generate the S expression. Essentially, all we need to do is to call this procedure with the right list of file names, and then we get the S expression. Okay, so there are a few limitations to G expressions. So the first one, and it's a bit embarrassing, is hygiene. Well, the GXP system doesn't pay attention to hygiene yet, and I'm going to talk a bit about it later, but yeah, that's kind of a problem. It's okay in practice, we can live with it, but it's embarrassing. It doesn't pay attention to modules in scope, right? So we have this with imported modules form, which talks about modules that need to be available in the CH root, but we don't have a way to express modules that need to be available in scope in terms of scheme, right? There is currently no serialization of non-primitive data types. Maybe that could be added later. And there's also no good debugging story. Like if you use hop, so hop can generate JavaScript code, and if there's an error that occurs in the client-side code, you get a backtrace that shows you the source inside your scheme code from which the JavaScript was generated, which is quite convenient. We don't have this kind of thing here. So if you get an error inside generated code, well, you get a backtrace, but you don't know where the source was. So that's not so great. So this work was influenced by several other works. I'm going to mention them quickly. So the first one, obviously, is syntax case. So there is a parallel to be drawn, I think, between syntax objects and gexp. I mean, the spirit is the same in that a syntax object basically adds additional information to an S expression, essentially. It adds contextual information that is required to, for hygienic expansion. But yeah, again, staging with GX is unhygienic, so there's also a big difference here. Then if we look at metascheme, metascheme is exactly what we would need in terms of hygiene, right? I mean, it's hygienic staging. That's exactly what we want. But the problem is that looking at the proof of concept by Oleg Kiselyov, it's very nice, but it's also a bit simplistic in that, so first, it doesn't pay attention to modules in scope either. And it's also, the question is, how do we determine in real life which bindings, which forms create new bindings? In the proof of concept here, there is only let and lambda that add new bindings. And this is obviously a bit limiting, right? This is not going to work in practice. So my guess is that we would need some sort of integration with the macro expander so that we can make sure we know exactly which forms are going to introduce new bindings. But again, I'm not very clear on how to achieve this. So I would welcome your input on this. Now if we look at hop, so hop has been influential in finding the right symbols because hop also uses tilde and dollar. So this is an example of the hop rape framework where here is saying that this is client-side code. So this form here is going to be compiled to JavaScript to be executed in the web browser. And this dollar form here means we are referring to a server-side value. And in this case, the server-side value is a service. So it's essentially a procedure with additional processing that makes it a valid HTTP service. So this is kind of the same problem space. The big difference, obviously, is that the stage code, the generated code, is JavaScript and not Scheme. And so that's one big difference. Then one thing that I really like about what hop does is that programmers can express which modules are going to be used on the client side. So if I remember correctly, you have a tilde import module form, which essentially tells that within this file, all the client code is going to require this module. And then everything happens automatically. One thing that is different is that hop implements tilde and dollar as compiler magic, I would say. So these are not macros. And as a side effect, those tilde expressions are not first-class objects. So I think, but correct me if I'm wrong, I think you cannot assign a tilde value to a variable in an arbitrary context. There are good reasons also for that, because since it's JavaScript, you cannot just do anything. Okay, and last one, obviously, is the Nix language, which is the driving source of inspiration behind Guix. So the Nix packager uses its own domain-specific language, which is also called Nix. And so that's what it looks like. And here you can see this dollar thing, which means escaping and getting a host-side value. So here what's going on is that I'm saying I want to refer to that file, which is local compared to the source file. And it automatically converts it to the long Nix store file name. So if we extend this example, I can create a second derivation that refers to the first one here. And this is automatically replaced by the Nix store file name. So a bit like unGX that we've seen before, right? It's the same idea. And again, the string contains all the information about its dependencies. So this is string interpolation, because the Nix language is only used to define packages. It cannot be used, it's a restricted domain-specific language, so it cannot be used to express arbitrary build instructions, for instance. So typically, the Nix language is used alongside with generated bash code, and that's where the string interpolation comes in. So strings retain information about their dependencies, and they are built into the interpreter. Of course, there are challenges associated with string interpolation and mixing languages. like for example, I'm sorry, I couldn't resist. This is an example of a problem that happens, when you generate strings that actually represent another language's program. You have to make sure you escape things correctly or things go wrong. So that's kind of a problem. Okay, so to wrap up. So in summary, Guix provides functional package and operating system deployment. It's just a normal scheme library and toolbox, right? Nothing special here. And it's also a multi-tier scheme system because we use scheme in all sorts of different places. And, there are lots of other niceties that would be worth talking about, but, like the system service architecture and services which are also written in scheme. I mentioned the Shepherd, which is PID1. There's also mcron, which is a cron replacement written in scheme. And the fact that it's written in scheme makes it interesting because, again, we can use staging. There's monads, there's Emacs integration, there's test suite, a whole system distribution test suite, there's distributed deployment. And again, these things involve staging as well, right? Because we have scheme in different places, so we need a way to generate this code. And so it kind of sounds like we're making, the list machine or the scheme machine again. So it's exciting. Okay, so this is it. So join us now, share the parentheses. You can install the distribution either on top of your distribution or as a standalone system. You can use it, report bugs, packages, and I would love to hear your ideas in terms of scheme programming and everything. I need your help. Thank you. Do we have time for a question?
It's exactly three. We have time for a few questions.
Yes?
So if you compile the same exact configuration on two different machines, will you get the same hash value?
Yes, if you compile the same config, you get the same hash value.
So right. Does that mean you can cache compilation and just have a server somewhere that pulls down?
Yes, exactly. You can cache compilation. We have a Guix publish command which publishes all your GNU store directory over HTTP. So if you were on a local network, you could use that. On one machine you publish things, and other machines can directly use it, like a mirror, basically.
How do you make sure you can trust that? In other words, so for example, the time might be part of the binary that's generated.
Timestamps and stuff. Right. So yeah, we're also involved in the reproducible builds project. And so we try hard to make builds reproducible because, we have all the infrastructure in terms of isolated build environments to facilitate it, but still there are cases where, you can have timestamps like you're saying, so it's not reproducible. But we have tools also inherited from Nix where you can essentially build the same derivation multiple times and see if you get the same result. And so you can fix timestamp issue typically. We also have a tool called Guix Challenge, where you give it several servers that provide binaries, and it will report on binaries that diverge, that have different contents, right? So let's say you build Guile locally, and you have 3 servers that provide Guile binaries. You can check that they have the exact same contents as the one you obtain locally. Yes?
How do you put the package? I guess there's something about the hash. Do you download packages by the hash? Is there any extra?
So how? Yeah. So there are two things here. So one thing is binary packages, and the other thing is the recipes themselves, right? So for binary packages, they have to be signed, right? And in your local installation, you say which public keys that you trust, right? And you will only install binaries that are signed by one of your trusted public keys. So that's for binary packages. And then the problem of recipes is a bit different. Essentially, Guix itself is all in a Git repository. So you need some sort of way to ensure that your Git checkout is genuine, right? And so we've been signing Git commits for a few months now, but the thing is, we still don't have the right mechanism to actually authenticate a Git checkout. And that's because it turns out that few people actually do that, as weird as it may seem. So we need to build our own mechanism to make sure that when you do a Git checkout, you get only commits that are signed by one of the authorized Guix developers, essentially. Does that answer your question? Yeah. Oh, yes. Why base 32? I don't have a good answer. It could be base 64 indeed. Yeah, right. I mean, it's just actually the base 32 form that you see in the recipes is a macro that generates a byte vector, you know. So we could simply have a base 64 macro that generates a byte vector, and that would be the same, right? Yeah, that's probably a good idea actually. It would make lines shorter. Yes.
I have a little bit of a provocative question. I'm not sure I fully understood the motivation for the problem you are really trying to solve. I'm a happy Debian user, and I can live with Debian package system, so I'm not sure I see who would be interested in replacing APT. And as a developer, when I want to provide package for someone else, these days I create a Docker stuff, and I can even send it to people using the Mac OS or something like that. So I don't really understand where you see.
That's a very good question. So why would you want to replace APT or RPM? Well, the thing is, APT or RPM are imperative package managers, right? They work by modifying the state of your machine until you get what you want. But that's very rough, right? So there's a parallel to be drawn between, imperative versus functional programming and imperative versus functional package management, right? And the main problem is it's especially acute for DevOps, right? DevOps, they typically need to deploy a very particular machine configuration on a number of systems. And if you do that using imperative package managers, well, you're never completely sure that you have the same configuration everywhere. So if you look at systems like Chef or Puppet, they try to get around it by, trying to run the right commands every time, and hopefully it's going to be in the same state on all the machines. But, that's very hackish. You're still not sure that you have the same values in functional terms. You're not sure that you have the same configurations. So that's one thing, DevOps. And also as a normal user, I must say that I'm very happy that I can roll back my user profile configuration or my system configuration anytime. That's a safety net that I wouldn't live without now. Because I know I can try out crazy things, I can switch kernels, I can switch configurations, whatever, and I boot, and if there's a problem, well, that's fine, I reboot, and in grub, I select the previous configuration, and I'm fine. So as a user, I think that's pretty cool. With regard to Docker, the problem with Docker is that you're essentially distributing opaque binary blobs, right? So, that's a problem in terms of user freedom because you don't really know what code you're running. You have no simple way to verify that those binaries correspond to what you want. And that's also a problem in terms of composition because you have one Docker image with a particular application inside of it, and you have another Docker image with a different application. And ideally, they would share the same libc, the same GTK, stuff like that. But you're not able to do that, right? So to me, these are a bit problematic, I would say. Yeah. Yes. Last question.
May I upgrade a package, and I know that it provides the same API and API with the previous package and without rebuild every dependency?
Right. So yeah, that's a good question. So one problem of this functional approach indeed is that if you change libc, let's say, then you have to rebuild everything that depends on libc, which is kind of a problem, especially if you consider security updates. So what we do in Guix is that we have what we call grafting, which allows you to simply build a new libc, and then if you want to run, I don't know, your NTP server with the new libc, you don't need to rebuild NTP and all its dependencies. Instead, you simply graft the new libc inside NTP. So you create a new value, if you want, of NTP, but instead of referring to the old libc, it refers to the new libc. And so that works by doing simple substitution, right? Text substitution in the binaries. So it may sound a bit hackish, but it actually works pretty well in practice, and that allows us to avoid rebuilds, especially, you know, full rebuilds due to security updates. Yeah. Okay, thank you.